Um, Not too many of you here, but we'll go ahead and get started because I do want to make. Maybe I'll wait 30 seconds. I guess I'm 30 seconds early. I know, right? 5 minutes, maybe. All right, so I wanted to make an announcement. I'm going to make this announcement for the Organic 1 students as well. Next spring, this upcoming spring, I know you guys are starting to register for classes now. Have you guys started already? Well, you're going to be starting registering for classes soon, I think. One of the things that I did last spring that I'm planning on doing again this upcoming spring is we're trying to do a pilot laboratory course based upon the chemistry that we do in my lab. So the chemistry that we've developed in my laboratory basically gives access to these molecules that seem to have a lot of broad bioactivity. And the chemistry is rather short. In fact, last spring we were able to make, I just had 6 students, I had 3 of them make one class of this molecules, the other 3 make the other class, just to sort of compare yields within students. This upcoming semester I'm going to try to expand it a little bit more. I don't know that I can do more than 6 students, but at least everybody will make their own individual molecule, and we're going to try to get into a little bit more medicinal chemistry-based studies. So it's a laboratory type course. The sort of idea is, from my standpoint, is can we do the chemistry in a 4-hour lab period, right? Like how practical is it? From your guys' standpoint, you'd be helping me out with that, but you'd also get to actually do some real chemistry that could be useful. So if you're at all interested, let me know. I'll probably post something on my website, but it's meant to be like, again, at this point we're sort of filling it out. My vision was that it would be a sort of a potential alternative to like the Organic 2 labs. I know you guys spent a lot of time doing like unknowns and stuff like that, and so I thought that perhaps this could be something that could maybe take the place of one of the sets of unknowns, or it might be something that could be a bigger part of it or something as well. I just thought that it's a type of class that gives students more actual synthetic experience, get to learn a little bit of new chemistry that's kind of cool, and hopefully, again, we didn't work out that well last year. We made the molecules, we were successful in that, but then when we tried doing some enzymatic inhibition assays, it didn't work out so hot. But we may do some different things this year. We may look at like, I'm interested, there's subtle pKa differences between these. I'm interested in potentially measuring the pKas of these various things. So anyways, I'll post it. Now I'm thinking I should have brought the day. I think it's going to be Tuesday afternoon, but I'll let you guys know in advance. So it's one of those things where you'll just, if you're interested in it, let me know, and you're going to want to make sure you don't have another class at the same time as that. Okay, so just keep that in mind if you're interested in that. I'm only going to have a certain amount of students. I do want to give priority, though, to students who are interested in careers and research. So just keep that in mind as well. Okay? All right, so today we are going to finish up Amines. Oh, so I guess one more announcement to make. Next week, starting on the 3rd, I think, it's going to be the quiz 3. And the week after that is the second exam. So just pay close attention. Quizzes and exams are coming up. So the quiz is going to cover everything through this week, right? And then the exam is basically going to cover all the reactions. So the exam is effectively going to be it's really going to be it's going to be, unlike the first exam, which will be focused a lot on Organic 1. This will have an element of Organic 1 to it, but now we've learned a lot of reactions, and so it's basically going to cover mostly Organic 2 reactions. But you can't really know Organic 2 reactions to an extent without Organic 1 reactions, so be prepared for that. Like, for example, synthesis problems will often rely upon your ability to know the Organic 1 chemistry, so again, remember that this is all sort of additive, so be prepared for that. Now you guys know how valuable I see mechanisms, make sure you're very up on mechanisms as well. So, all right, so today we're going to focus on amines. Probably today and tomorrow we're going to focus on amines. And so At this point, you guys have probably heard the name amine enough that you sort of know what an amine is, right? So this is an amine. It's a nitrogen-containing molecule. As drawn here, this is what would be called a primary amine, because it's bonded because the nitrogen. It's a little bit weird because it's a little bit different than what we refer to like alcohols. With alcohols, we're often referring to the substitution of this carbon. With nitrogens, because there's multiple different substitution patterns that you can have. You know, you can have, this would be a secondary amine, right? So I guess just here, right? If it's bonded to two alkyl groups, we sort of have a secondary amine, and as you might imagine, if you've got 3 R's to it, this is the tertiary amine. And again, depending upon what the amine that you have is, we'll see there's some different chemistry that can sort of result from here. But we've seen different types of amines at various times throughout the semester in different contexts. And this sort of chapters on amines that we're going to discuss really sort of completes the discussion on the amines in terms of a way in which you would otherwise want to know. Much like alcohols, you guys, those of you who took the class with me, or even if you didn't, sort of one of the ideas behind alcohols and one of the sort of points to make about alcohols is that, and we'll draw a parallel to amines here, is that in one way you can take alcohols and you can convert them into leaving groups, right? So, for example, if you have it in the presence of an acid, right, alcohols can effectively go from can basically be converted into perhaps a good electrophile, right? And so we've seen instances where alcohols can become electrophiles. We've also seen cases where if you treat this with, say, for example, a base, right, you're going to get to an alkoxide, right, and that alkoxide is going to be behave as a nucleophile. Right? So in terms of synthetic intermediates, we've previously seen how alcohols have this sort of versatility to them. It also makes them kind of challenging to work with, right? Because sometimes you might want them to behave as a nucleophile, but you have to be careful about this electrophilic activity. Oftentimes, you know, we've seen instances where there might be another functionality around, like for example, a Grignard reaction, maybe you're trying to add it to a carbonyl and you have to protect this because you have to be worried about that. So with that versatility, right, comes a little bit of trickery and difficulty in terms of working with it as well. So oftentimes in the synthetic chemistry lab, in the case of alcohols, you know, we'll usually make it, but oftentimes if you read a lot of synthetic chemistry papers, they almost never take an alcohol through several steps as the free alcohol. They almost always protect it. There are examples otherwise, but in general, just that difficulty of having to work with it as a problem. Amines are actually even worse. Well, they're worse in terms of the sort of difficulty sometimes to work with them. There's often this thing that's said among synthetic organic chemists that however long you think a total synthesis will take you, like if you're trying to carry out a synthesis, they say however many amines are in there in that molecule, add another like 2 months per amine or something like that. So there's a difficulty associated with amines. Again, for the same reason in the case in which they can behave in both this sort of nucleophilic, particularly as a nucleophile. But as we're going to see throughout this chapter, as you might imagine, an amine by itself can behave as a nucleophile, right? So we've seen cases like this. Again, we have these lone pairs. It can be rather basic. And so in a way, just in of itself, this molecule kind of can be a nucleophile or a base, right? And again, you can make that argument, you know, alcohol certainly as well, but in the case of amines, it almost becomes a little bit more likely that it's going to behave as a nucleophile. Again, you can sort of make a pKa argument for it. Again, amines are basic, right? You think about a molecule like triethylamine, and that's basic, whereas water, you sort of think about as neutral, so there are those subtleties. But certainly you can take it and even make it a better nucleophile or better base, but you need something fairly strong, right? As we've seen in the past, something like sometimes what you'll use is butylithium, something super, super strong. Butyllithium, it's basically, you know, again, the pKa is like 50, and oftentimes you'll use something like butyllithium to generate, to basically take off that other nitrogen. In this case, now you have an even stronger nucleophile, an even stronger base. But you actually can take these molecules, and we'll see this a little bit, you can take amines and you can get them to behave as leaving groups analogous to alcohols as well. And we'll discuss this a little bit, but I'll just say for now, because we'll see this a lot, there's going to be a lot of different cases with this. I'll just say N, and then I'll just sort of leave it blank. But there's various modifications to electrophiles. And a large part of the chapter is actually devoted to this. We're going to see there's different types of ways you can take amines and treat them and functionalize them and convert them into different types of electrophiles. And some of these are like really valuable. Like we'll see, for example, nitrogen, right? You can't get a much better leaving group than N2, right? And so one of the things that we'll see, for example, is leaving as N2. Another thing that we'll see it leaving it with as sort of amine. If you get the ammonium, we'll leave it as the amine. And so much of what this chapter is going to be involved in is really going to be the functionalization of this as electrophiles, and also how we can sort of make amines. And so if you read through the amine chapter, there's really two themes. It's synthesis of amines, and then there's this sort of chemistry of amines, but really the chemistry of amines that they're referring to are almost always like what you can modify them to become. So it's certainly the chemistry of amines, but the intermediates that we generate aren't necessarily going to be the valuable synthetic intermediates that we're going to be working with. Okay, so in terms of chemistry, that's where we're going to sort of discuss. So I just want to sort of draw that parallel. There's going to be differences, but again, this is going to be the theme in terms of chemistry. So in addition to our sort of primary, secondary, tertiary amines, we should recognize that there's other types of amines that we'll see time and time again that are worth keeping an eye on, that are perhaps a little bit different, but are at least worth knowing the names. And then I'll sort of move on to chemistry, move on to hybridization, and I'll move on to chemistry. So some of the amines that we've seen quite a bit that are fairly common. This one right here, does anybody know what this is? This is pyridine. Right? Pyridine is a nitrogen that's sort of within a benzene group, right? And so the nitrogen is in fact sp2 hybridized. Sort of lone pairs out there that's going to behave as the base. Pyridine is what we often consider a mild base. It's not the most strong of bases. It's got pKa, and you'll see compared to some of the others, equals 5, right? And so if you take pyridine, it will react with sort of things that we consider acids, like you can take acetic acid and treat it with pyridine, and you'll get the pyridinium salt, right? The pyridinium acetate salt. But you really got to go up to really stronger acids before you start to see this. And this is fairly the case with amines, but you do have this little bit of a window here. Other bases that we see a lot, triethylamine, right? So this is your standard tertiary amine. This has a pKa that's much higher, okay? So it's a little bit of somewhere around 11. So it's also fairly more basic. But there's actually another property that you often see behind these tertiary amines in something like pyridine. From time to time, you'll see molecules, and this sort of becomes exaggerated with derivatives of these as well. A molecule like pyridine, right, can actually behave as base, but as you might be able to tell, it's sort of got all this wrapped out in that lone pair coming out, and it also behaves as a decent nucleophile as well. Even though it's not charged, Pyridine can behave as a good nucleophile. And oftentimes what you see, there's a molecule called dimethylaminopyridine. You might have brought this up in the past, or you might have seen this in the past. This is dimethylaminopyridine. It's basically a derivative of pyridine that's even a better nucleophile. And so you'll just see this abbreviated as DMAP. And DMAP is a really good amine, what we would call Lewis base catalyst. So you'll actually see this work quite a bit. I'll give you an example of where Lewis base catalysts have actually come into play. So Danielle's up back there, and I'll show you an example where DMAP worked out pretty well for us. So one of the things that Danielle Hirsch, for some of you guys have in class, one of the things Danielle's been working on in our lab is how you can get, we're working with these molecules, again, these are sort of bicycles that we're working on in our lab, and one of the things that we've really haven't really been that good at with our chemistry is bringing in substitution at this position. And what Danielle has found is that if you put an iodide there, you can actually functionalize this. The thing that's interesting, right, is you see a molecule like this iodide, and it kind of looks a little bit like sort of a conjugated acid chloride, right? It's sort of an iodide over here. You can imagine it the same way if that was a carbonyl, that would look like an acid chloride. But what she found was that when she takes this and she treats it with methanol, just to try to get methanol, for example, to displace that iodide, that was something that she was interested in, actually didn't work at all. She wouldn't get any chemistry. But when she added a molecule like DMAP, it actually worked very well. She had to heat this a little bit, but she was able to get this to work. And the interesting thing is this is what we would call Lewis base catalyst. So this is more basic than the methanol. Right, and this comes down and we'll kick off the iodide. And what you'll effectively get to is this new compound, and as it turns out, you can go through the same mechanism. But now you've got this sort of new complex, and then it turns out that at this stage, now the methanol can actually add in a little bit better. So methanol doesn't add into the iodide, but it turns out that this amine will, and then suddenly you can, effectively go through a parallel. I won't go through the whole mechanism. What she was able to do is actually get that methanol on there. So you'll see this a bit, right? We've seen Lewis acid catalysts in the past, right? We've seen examples where you have some type of Lewis acid, something that will accept pi electrons. But amines will often make up what we call Lewis base catalysts. So this isn't really discussed too much in the book, but you can sort of see it, and you can sort of see examples of where it's important. And oftentimes you'll see acid chlorides, for example, the reaction will be accelerated if you want to perhaps make an amide or something with dimethylaminopyridine. On the flip side, triethylamine, it's got all these appendages on it, and it's not, and the whole reason why it has value is it's actually not that good field. Right. Why does the nitrogen now kick out? Why? I mean, it probably has to do with kinetics. So it's the nitrogen is the sort of net result product. This is the most stable overall product. But the uphill barrier to get the methanol to add in here is just too high in energy. But the nitrogen, yeah, it is a little bit counterintuitive. I get that. It's like, well, it adds in better, so why does it fall off better? This is like a trademark of sort of Lewis-based catalysts. And so it's fairly interesting. But again, you'll see this time and time again. There's a lot of chiral Lewis-based catalysts as well, like quinine-based molecules that allow stereo induction. So yeah, it's a little bit, I get that that's a little bit counterintuitive. It adds in, but then it's easier to come off, but that's sort of a hallmark of Lewis-based catalysts. And nitrogens, again, you could rationalize it based on there being a charge, but this is a better leaving group than iodide. So, okay. Likewise, molecules like triethylamine, while sort of aromatic pyridines and such like that, you'll see them built within things like Lewis bases. A lot of times for like Bronsted bases, if you just want something that's going to pluck off a hydrogen, you'll stick with molecules like triethylamine. And in fact, there's even bulkier versions of it that you'll see. Oops. This is a molecule, diisopropyl ethylamine. This is often, you'll see it from time to time again. It's diisopropyl ethylamine. So you basically taken the three ethyls and you've made one of them a kebutyl group. And this is often sometimes referred to as Hünig's base as well. So again, the point that I'm trying to make here is that within amines, you'll oftentimes see the sort of alkyl amines behaving as Lewis bases. Sorry, you'll see the sort of aromatic amines behaving as sort of Lewis bases. And you oftentimes see these sort of tertiary amines behaving as Bronsted bases. And again, it's that these can be nucleophilic. They will sort of add into things. You have this sort of lone pair sticking back, and there's derivatives that make it even better. But then in cases like triethylamine, which is a fairly standard one, that's a better Bronsted base, and people have taken that and made even better Bronsted bases. Again, you bulked it up so that it will only behave as a base. So you'll see these types of amines as bases in chemistry, and you'll see other examples of amines as well. There's molecules called, there's a few others that you'll see. Heteroatoms like pyrrole. This is pyrrole. As you might imagine, in the same way that pyridine is, you'll see pyrrole sometimes used as a Lewis base, but Lewis base. There's often even better ones like imidazole, where you simply throw nitrogen into that. You may see imidazole a while. Imidazole is oftentimes used, specifically N-methyl imidazole is used a lot with BMAP. So you'll see examples like this with amines from time to time, just within organic chemistry. And the other one that I'll sort of show, we actually use this base in our lab, or derivatives of it, is aniline. So aniline's somewhere in between, right? The nitrogen's not part of it, but the lone pair is sort of pulled back into the pi system. So this is aniline. So again, I'm not big on sort of nomenclature, but I'm just showing you guys these because these all represent amines, and you'll see them used in sort of diverse, as I sort of said earlier with amines, having diverse activity and potentially being good even within the classes of amines that you see. Simply Lewis base versus Lewis acid, subtle differences in amines will give you both of these sort of effects. Okay? So this is just to show you different types of amines and how different amines will often be chosen based upon how you want and what you want. Okay? Now, one of the things about amines, okay, that's worth noting that's a little bit different than other molecules, before we get into the chemistry, this will be the last thing, it has to do with the hybridization of amines. Okay, and an example that we've seen in the past, it's sort of an amide, but you'll often see it with a molecule like pyrrole, right? So we discussed with an aromaticity, right? You have that nitrogen there with its lone pairs, and this can behave with aromatic in the same way, but there's a lot of cases where that nitrogen, if you were just to look at it, you might assume that it's sp3 hybridized, right? But knowing the sort of resonance forms and the localization that can be a part of it, it's actually sp2 hybridized. And so the lone pairs, you have to really, when you're starting to think about the hybridization of amines, you have to consider the lone pairs and where they might want to be, right? And so a perfect example of this, I think, is amides. Okay? Now, if you have an amide, right, again, an amide has its own class name, but effectively it's an amine that's part of a carbonyl system, as a good example. This is the perfect example of a nitrogen that is in fact sp2 hybridized. Right? And again, one of the reasons why we can sort of realize this is when we think about the resonance form of it. Again, these lone pairs can create this sort of resonance form here. And it turns out this is a fairly major resonance form in such a way that, in fact, rotating around this nitrogen-carbon bond is very, very slow, right? So you can often think of amides in the same way as you think of alkenes, right? So if you have a molecule like this, we could have it drawn with the R here and the proton here, but we can also draw it the other way. Right? So you see I just switched the R and the H. Now, in standard systems, we might not really think that much of this, right? Because we would assume that the rotation is actually fairly quick. But in the case of amides, we actually have names for this, right? So this would be more, just draw the standard amide. We draw like this. There are actually two different forms of these amides. And as you might imagine, the way that we refer to them are sort of like cis and trans as well, right? And so, again, the nomenclature isn't that important, but the point is that you have these two different forms, and the rotational barrier is very slow. Again, because there's such a high percentage of it as this double bond. As we know, you don't rotate around double bonds, right? So in order to rotate, you have to effectively break the plane, have this become sp3 in order to rotate around. And so there's very slow rotation around these. A lot of times in NMR, when you do chemistry with amides, you'll oftentimes get what we call rotamers. So on the NMR timescale, you'll see a little bit of this and a little bit of this. In the NMR, you'll assume that you have two different molecules, but it's actually just one rotamer of one and one rotamer of the other. And sometimes what you can do is just heat the NMR tube so that the NMRs will have like heating apparatuses in them, and you'll just bring it in and you'll see it resolve because you effectively allow the rotation around that. So that's an interesting artifact of amines, is that oftentimes if they can sort of delocalize with electrons, they'll become sort of sp2 hybridized, and within that there's a lot of features that are involved with it. So that might make sense, right? I think from a resonance standpoint. Again, we've seen this. Yes, Felix? Yeah. The question is, can nitrogen form 5 bonds? In theory, I guess yes, but you have to pull onto its 1s orbitals, or even pull into the sort of 3D layer. So unlikely. You want to treat it like carbon. For your guys' sake, I've never seen nitrogen with 5 bonds to it. Let's just say that. In theory, could there be a situation where you might be able to generate nitrogen with 5 bonds to it? Maybe, but that's going to be a highly, highly, highly unstable intermediate. So don't ever draw 5 bonds to nitrogen. Mm-hmm. No. You'll never have 5 bonds to nitrogen. Like parole? No, it'll still be 4 bonds to it. Yeah, it'll keep going around. You'll never get it. You won't put it under the nitrogen. Let's just say that. So now this negative charge will go over here, and then will go over here. So you actually can do negative charge in each of those positions. Keep pushing those electrons. But yeah, you'll never get 5 bonds to the nitrogen. Phosphorus, yes. But phosphorus, you know, you can pull into the D electrons. Like a lot of times in order for you to, again, the whole reason why you can only have 4 bonds to a lot of things, that's mainly when we're talking about sort of second row, so boron, oxygen, carbon, nitrogen, those sort of elements. And again, that's because they don't have the ability to then go into the D electrons. Once you can start using D electrons, now you effectively have 16 electrons to choose from. But in this, most of those cases we're dealing with, there's only 2. So, okay. All right. So anyway, that will hopefully make sense to you guys. But there's this other kind of bizarre thing about amines that I remember when I learned about it, I was kind of taken back by. But if you think about amines, right, unlike ethers, right, if we have, say, R1, R2, R3, this molecule is actually chiral, right? So it's just the extra. So like carbon, it can have 4 different things bound to it. Oxygen, you know, I guess if you protonate oxygen, then you can have 4 different things to it. But in the case of nitrogen, just sort of neutral nitrogen, the lone pairs are effectively in one sort of direction, and then you have the other groups. And so this molecule and this molecule, again, this is just you just rotate that around, you see it's the mirror image. These 2 molecules are in fact mirror images of one another. They're enantiomers of one another. They're non-superposable. So if I just go ahead and rotate that around, maybe that's what you do. Right, if I rotate this around, what you'll see is right, so the R1 is just going to stay in the back and just rotating a plane of board. You can see that this and this are mirror images of one another, but they're in fact non-superposable. Again, they have 4 different things bonding to them. One of the things that's interesting about nitrogen is it's often very, very difficult to get chiral at amine compounds. Usually there may be some stereochemistry that can relate to it, but in the case of amines, you can actually do something called nitrogen inversion chemistry. So sort of chirality at nitrogen can actually racemize fairly readily. So you can actually planarize this molecule these electrons can effectively go what we call an inversion, so the lone pairs can effectively, in a way, kind of weird, but end up down here. Right, and then once this relaxes to the sp3 hybridized form, you can actually get the enantiomer. So that's just something also to keep in mind. It's interesting about the hybridization of sort of nitrogen is that you can actually undergo this nitrogen inversion. And effectively racemize that nitrogen. So again, that's sort of an interesting factor about nitrogen that's sort of worth keeping in mind. Okay? All right, so on to chemistry. Okay, so this is just some background of nitrogen. It's mostly just sort of interesting factors, I think, that's worth knowing about the sort of physical organic side of this. And I'm not sure if it's going to bear itself too much within synthesis, but I think it's, the book discusses it, yeah.
For the mix, depending on the temperature of the solvent, is there a preference for
I'm sure that it's probably going to depend upon the sizes of these groups, right? The bigger that these 2 are, the more likely this will want to be on the other side. So usually you want it this way, because the oxygen is fairly small. But yeah, I mean, like you're saying, could there be, say, for example, hydrogen bonding and stuff that brings back here? So generally, it'll exist in this kind of like the Z form, if you will. Okay, so we'll get into some chemistry now, and again, back to what I had sort of mentioned earlier, keep in mind this idea that there is a parallel that can be drawn between amines and alcohols, at least in terms of your sort of potential use for them. So probably the basic reaction that you can imagine with an amine, right, is let's say you took a molecule like ammonia, right? If you want to start, let's start by talking about synthesis of amines. Again, if we're going to have amines in our molecules, amines are very important. I think something like 80% of drug molecules on the market have nitrogen in them at some point, so they're obviously a very important component of life, right? And so, as a synthetic chemist, it's often important that we're able to synthesize amines. And so, the probably most basic for the sort of most basic way that you think about doing and making an amine would be to simply take something like ammonia and treat it with an alkyl halide. Again, we've seen the same type of situation with, say, for example, alcohols, right? You can take sodium hydroxide, treat it with an alkyl halide, and you'll get to the alcohol, right? And so that'll work to an extent, right? That'll work to an extent. Your nitrogen can attack, it can pull off the bromide. You'll end up with an ammonium bromide, right? And then perhaps you take this molecule and you treat it with, say, for example, a base, right? So if this is your sort of first step, and then your second step is some type of base, you can imagine getting to that molecule, and certainly you can do this, right? You can certainly take an amine and treat it with an alkyl halide. You can get to alkylamines. That's not a problem. The problem really comes that it's going to be a fairly messy reaction, because in addition to alkylating once, it turns out, right, that if you have a molecule like this, okay, while this is protected, well, keep in mind there's a lot of other amine around there. And so what can happen, right, is that if you have, say, for example, so if we add, say, for example, NH3, right, you'll go this way and NH4 that way. So again, you might have some ammonia in there, the ammonia can pluck that off, you get some equilibrium, and then suddenly this will start reacting with the bromide as well. Right? And then that process can sort of keep going, right? You can imagine getting di-substituted amines, you can get tri-substituted amines, and so this sort of process can go on and on and on and on. So while in principle you can certainly do this chemistry and you might be able to get some of this, you'll get a mess of other compounds that's going to make it kind of synthetically not that useful. And so in general, this is not the way to synthesize amines. Okay? We have other ways to do this. And some of these have been very analogous. Some of these you might have seen in the past. I know I taught this reaction when I taught synthesis 1. But one of the ways that you can make amines is through a reaction called a reductive amination. Okay? A reductive amination, we're going to switch up effectively what our nucleophile is. Actually, let me just, before we get into reductive amination, if we wanted to use an alkyl halide, and we want to get to primary amine, we can do this. You guys remember what we do? Well, that's one way, but that's not. That cyano's going to add another carbon there, right? Because there would be CN. Certainly, a cyano could make an amine, but we'd want to have one left. But just something where if we have an alkyl halide, we want to swap out the halide for an amine. We've learned it this semester. So excess of ammonia certainly work. That's a stoichiometry issue. So the point that's brought up is you keep a lot of this in there such that you're always going to have a lot more of this. So certainly that's one way that you can do it. Just have a ton of ammonia and just don't allow, just stoichiometrically speaking, just have a lot more ammonia than this. So that's good. I'm glad you brought that up because stoichiometry is one way that you can handle that. There's another way that we learned it, yeah. That's the second step. What's the first step? So your conditions, so you're talking about hydrazine, right? So hydrazine is actually, that's going to make a double nitrogen if you did it with this. But that is a reagent in a synthesis of amines that I'm thinking of. OH can be a reagent. But remember the Gabriel synthesis? Guess not. Remember this? Right? So if this is the first step, and this is the second step, I just want to bring this up because it is a way that you can do this. And then the second step in this would be hydrazine. And again, what happens is this becomes a good nucleophile. Right? And so you've effectively protected all those other nitrogens. It's nucleophilic enough. And then what you do is you take this and you treat it with H2N and H2. Right? And this is just going to hydrolyze the system off. So it's just going to attack there, and you're going to be left with the primary amine. So this was Gabriel synthesis. So this is one example. So as I'm sort of going forward, showing you some ways around this, we have seen this semester this way, and so I just wanted to remind you guys of this option as a method for synthesizing primary amines. Okay? But an alternative way to do this, there's a couple ways, and we'll go through those as well. So one of these is a reductive amination. Okay? Reductive amination is a process where, I feel like have we gone over this semester already? Right, so if you have an amine, right, and so this is always going to lead to a primary amine, so this is probably a good way to do it if you're trying to just make a primary amine. Let's say you're trying to make, for example, a secondary amine, so you've got an amine already, like this, with some R group on there. What you'll do is a two-step process. The first thing that you'll do, if we give that R1, I'll give this R2, you're going to condense this reaction with an aldehyde. So what happens when you take amines and aldehydes and mix them together, maybe with a little bit of acid? What's going to happen? What's that? Right, so you're basically going to have this replace the oxygen. So you're going to generate the imine. Okay, and that's an imine. Okay, and then what we have to do is what? The sort of the reductive part of the reductive amination, right? So now we have to sort of reduce this. Now the reagent that you use in a reductive amination, you could use other hydride sources, but generally the go-to method in a reductive amination is generally sodium cyanoborohydride. So it's basically sodium cyanoborohydride. So it's sodium cyanoborohydride. This reagent is a little bit, I think, milder than your sort of standard NADH4. Usually you run this reaction, sodium cyanoborohydride, you'll run this reaction like methanol or something like that, or some type of protic solvent. The reason is that while the imine is actually less nucleophilic than your standard carbonyl, If you have, say, something like methanol in there, or sometimes even a small amount of acid, what you can begin to do is build up a little bit of positive charge here, which is going to increase the delta positive charge here. So in things like protic solvents, you'll often start making hydrogen bonding and stuff around here, which will actually make it a little bit of a better electrophile. But the point is, what you can do is now you can, you can just think about it as, if you guys wrote down sodium borohydride instead of sodium cyanoborohydride, I really wouldn't care. The point is that you make an imine, and then you do a reduction. I think that's the more important point, is that it's a reducing agent. It's a hydride source. So you can think of it just like making an imine, which you should know, and doing a reduction, which you should know, okay? So this is one option. It's a particularly good one if you want to make secondary amines. That's your secondary amines. So again, Gabriel synthesis might be a good one if you want to make primary amines. If you want to make secondary amines, you probably want to go this way. But there's another few ways that we know as well that are generally pretty good for making. So this is probably the go-to way if you want to have like an internal amine. You can do it. I think you can actually do it with secondary amines to make tertiary amines as well. You just generate the iminium, and I think oftentimes in those cases you have you actually have the. I'm not sure, I might be making this up, but I'm pretty sure this is the case. If you have a secondary amine, you'll actually generate the iminium. And I think in those cases you actually use the sodium cyanoborohydride like in the reaction with it, so it sort of like traps it out, yeah. Sure. So in the case like I just sort of said, it sort of takes advantage of the fact that you can have that's a better nucleophile for the sodium cyanoborohydride. Sodium cyanoborohydride will not react with aldehydes, from my understanding. So via Le Chatelier's principle, sometimes you can do it in one pot. At least that's how I'd always learned. It turns out that actually when I went and ran this, I did effectively exactly what you're saying. When I've technically run this reaction in the past, it was a two-step reaction. So it was, I don't think I used Dean Stark, I think I used like molecular sieves or something. But the same idea, I sequestered water from this reaction, isolated the imine, and then subjected that to sodium cyanoborohydride. That was the time that I did it physically in the lab. But I'm pretty sure that you can do it all in the same pot. And I believe that the reason why you can do that is that the iminium that you form there is more electrophilic than the carbonyl. And so, again, via Le Chatelier's principle, you'll generate the iminium and you'll reduce that. I could be wrong, but I'm pretty sure that's the case. Yes? Yeah, I mean, I think, yeah, so LAH would probably work as well, too. LAH is kind of the big guns, right? Like, we actually had a fire in our lab with LAH, so it's not quite as safe. So it's sodium. Yeah, it would. I'm sure LAH would work, but it's safer to use the other ones. Yeah, Margo. We're going to talk about this. Wait a second. Nitroalkyl, absolutely. So we've seen, I think the point that Margo is making is we've seen other examples, and I'm sort of just filling in some of the blanks here. So we've seen other examples. Margo is saying nitroaldol chemistry. So we've seen examples with nitros. So if you wanted to do a sort of a nitromichael, right, and make that a nucleus, make that electrophile, or I think what Margo's saying is if you wanted to make that enolate and have that react, that would effectively be a source of it as well. So then you can just reduce the amine afterwards. So yeah, there's other options. I'm just sort of right now cleaning up showing the ones that this chapter has. Another way, the way that I've actually done more than not made amines is actually from azides. And so azides, as we've sort of learned, can be really good, like sodium azide. So sodium azide, as we've sort of learned, is an awesome nucleophile, right? Because it's charged. It's sort of like a pencil, right? It's thin, so it doesn't have any steric components to it. So it can come right in the back and displace the alkyl group. And what you can get to is an alkyl azide. Okay. This is a good way to do this. It turns out that it's not good if you're doing, azides are actually explosive, so if you're doing this on like smaller molecules, sometimes in the gas phase it can actually explode on you. But when it's bigger, it's pretty safe. And from these intermediates, there's a couple ways. The way the book discusses and the way that people actually do it, I've never seen people do it the way that the book does it, but the typical reduction method for azides that I've seen is a reaction called the Staudinger reduction. So it's basically triphenylphosphine and water. And what that will do is that will get you to this. Again, this is how people really do it. The book doesn't discuss it, so you don't have to learn that, but you can certainly use it. And if you were to do this chemistry in my lab, that's what you do. What the book this says is lithium aluminum hydride. Okay. Oops. Yeah, sorry about that. So in the case of lithium aluminum hydride, mechanistically at least, you can sort of think about this. You guys could probably think about a mechanism that gets this, right? Because what you have is, again, if you think about this being a hydride source, let's think through the mechanism of, again, the book doesn't discuss this mechanism, but I think you guys could probably come up with a decent mechanism. So let's do it. So if we had this molecule here, and I wanted to take it and treat it with a hydride, right, an H minus. And this was a mechanism problem, and it showed up on an exam, and you'd never seen it before. How would you go about thinking about how this reaction might work? Yeah. Yeah, and why else might you want to put that hydrogen there? Because there's a hydrogen in the nitrogen in the product, right? So, yeah, so what you may want to do is push that up there. So the thought was, from almost a kinetic argument, right, was well, there's a positive charge there. That's going to mean that there's going to be a good delta positive here, which means that the hydrogen can attack there, effectively pushing that positive charge onto this side. Okay? And at this stage, what might we then think might happen? Right, we've got our negative charge over here. Where do we want to push that? Making a triple bond. Now we've got 5 bonds to nitrogen, so we can't have that. So we're going to push these guys onto here. Right. That's going to generate the amide, right? And so that's probably the result that you're going to get from the from the lithium hydride reaction. And then again, when you quench it with water and so forth, and maybe an acidic workup, you're going to get here. But again, yeah, the group that loses is nitrogen. I'm not actually sure that this is the mechanism of it, but I think it makes sense, yeah.
Then can't we say from the negative charge of 19 why lithium hydride is not a good source? Because this is one reactive technically.
What's that?
Isn't this the reactive intermediate?
Which one?
Negative on 19?
This?
No.
This?
No. The answer.
This?
Yeah. The final product out of the lithium product.
Yes. Like a hydrazine derivative? That's great. I love your guys' thinking. Yeah, I don't know. It'd be interesting to see if that's a byproduct. So yeah, everybody sees what they're saying. They're saying, well, you got a new nucleophile here. Could that behave like the hydride nucleophile over here? It's an interesting idea. It turns out, and I'm going to digress here for a second. No, I'm not going to digress because I don't want to confuse you guys. I'll just tell you that in reality, this is a mechanism that can get you to the product. I bet you could all probably do the same thing with triphenylphosphine. The product that you're going to generate is triphenylphosphine oxide. If you want a challenging mechanism question, try to figure that one out. The problem is that the immediate mechanism that you might come up with probably isn't the right one. So if you guys went ahead and looked up the mechanism that is the real mechanism, it might not be the one that I would expect you guys to get. The mechanism that is actually true was not the first one that was thought to exist. So you can actually attack, if you look at the resonance form up here, you can actually attack this nitrogen as well. But anyways, if you guys want, if anybody's curious, try to come up with a mechanism of this. The product is triphenylphosphine oxide. Okay, could be an interesting, if you're interested in trying a mechanism that you haven't seen before, that could be a good challenge and practice for you. Okay? But again, you're not responsible for that. Yeah, just give it a shot. Just play with it. If you're curious, if you have time. You know, if you don't have time, you know, like don't do that at the expense of other things. But if you have some time, yeah. Can I use NaNH2 to displace this? So could I use sodium amide to displace that? You'd probably end up running into the same problem that you would with a normal amine. It's just that instead of the amine attacking, right, now you get that exchange of deprotonation, and that would attack as well. I would bet that would have a better chance of working than just ammonia by itself. But I would bet that it would still have some of those same issues. And the other issue is that depending upon what R group is, you might also start getting some like elimination chemistry as well. Yeah. Yes, and then yes. You could do that as well. Yeah, it's a reduction. Question was hydrogen and nickel. Yeah, that's enough. You can do hydrogen and nickel, and you can reduce that as well. That would be the workup, right? So you guys see workup, aqueous workup. Yeah, so you would probably treat this with a little bit of you take this and you dump it into water, and you're going to generate the primary amine. Okay, did you have a question?
In the last chapter, sort of like you can directly add the other one really anything to add nitrogen and reduce it, right? That's still
No, that's the opposite. You're going to make a nitro group.
yeah, then add and reduce the nitrogen.
Yeah.
That's really add.
I'm sure it's not. Yeah, I'm sure, you know, again, you know, you guys we were talking about nucleophilic aromatic substitution, right? We were saying that if you have a chloride, I'm sure you could add one of these nucleophiles, whether it's an azide or whether it's the Gabriel synthesis compound. I feel pretty confident that you could probably get one of those to add 1,4 and kick out the chloride. So, yeah, I never like when they say only way, or yeah, so yeah, I'm sure that's never the case. So, all right, so again, we have azides, and again, there's lots of ways to reduce azides. This is if you actually went and saw this chemistry being done in the literature, you'd see this reaction, Staudinger reaction. On big scale, it may be catalytic hydrogenation, as Margot's saying. The book chooses to use lithium aluminum hydride. But again, it's simply just a reduction. The point is that you get to this compound that's a higher oxidation state. Okay? All right. Okay, so that's how we can make them. Again, somebody else brought up cyano groups as well. So just taking to the next step, if you could do a similar sort of thing with a CN. But let's just I'll just show that one really quickly because somebody brought it up. Right? If I use like lithium cyanide, again, we've already seen this, right? But if you did this, then you'd end up with that cyano group there. Just notice the one big difference between these two is that if you reduce this, you can do that, right? You can go ahead and reduce this with, say, for example, LAH or probably nickel and hydrogen. I'll just say reduction. LAH, for example. But again, what's going to happen here is that you're going to end up with you're just going to get that extra methylene in there. So there is complementary value to the azide addition and the cyano addition, but what you don't want to make the mistake of doing, and it's fairly common, that's why it's beneficial to think through the mechanisms when you're doing the chemistry that you're doing, you should be able to see, okay, well, I'm adding an extra carbon here, and here I'm not adding extra carbon. So just be careful, because that's a mistake that you guys could make if you're not really paying attention to what you're doing. So they're not making, yes, there are both ways to make amines, but they are both effectively making slightly different variants of that amine. Okay? All right. So the bulk of the chapter, so this is the synthesis of amines, some which we've sort of seen in the past. But really the bulk of the chapter, as I saw it, dealt with how we can functionalize an amine and turn an amine into a leaving group. And what's kind of interesting about this is that I'll just say LG for leaving group. What's interesting about this is there's many different ways that you can convert them into leaving groups, and you'll see different types of chemistry depending upon whether it's sort of milder chemistry or highly reactive species. You can generate very strong electrophiles, or you can generate relatively tame electrophiles. And the one that is probably the most simple, right, is if you take an amine and you treat it with a mild base, like, say, for example, sodium carbonate, again, some base, and then something like iodomethane, excess. Yeah, we talked about earlier how when you start alkylating amines, you continue to alkylate it over and over and over again. And so what can happen is, and you can go through the mechanism, see this, alkylate, deprotonate, alkylate, deprotonate. What you'll get to is this ammonium species. Okay, and now this can actually behave as a decent leaving group. You'll generate trimethylamine, right? So now you can effectively take this molecule and you can treat it with a nucleophile. Right, and what you'll leave is the amine. So you can begin to effectively switch out compounds here to get new compounds. And I actually hadn't really seen this sort of amine chemistry done too much in the literature. Where I did see it, actually, I was teaching an advanced synthesis course the last couple springs, and like one of the fathers of organic chemistry, this guy R.B. Woodward, like I found that back in his day, and this was like back in like the 40s and 50s, he was doing this a lot. Like it was almost like this was his primary sort of leaving group for a lot of the chemistry that he's doing. So this is very classical. It's been used as a method for a long time to generate leaving groups. Again, trimethylamine is a gas, so it's kind of nice in that extent. Maybe from the standpoint of back in the day, they would then smell that, and it might be an indication that the chemistry is working. But this is used quite a bit. One area where you see it used that might be valuable for you guys is, say, for example, if you're trying to do an elimination reaction, right? So there is a reaction that uses this. So this would be for substitution chemistry. But where you'll see it sometimes is in a reaction known as a Hoffman elimination. Right? And so if you have an alkyl group, let's say, for example, you have an amine, right? Let's say it's a tertiary amine, okay? And you want to go ahead and do an elimination from this reaction. You went ahead and treated this with iodomethane, right? You would get to and at this point, we want to do an elimination, right? And really, we've got a couple options that we could go for, right? We can either go, we can either do the elimination from this proton here and generate this sort of external double bond. So if I just say HA, right? Or if I go HB, how you can sort of get that internal double bond, okay? And as you guys sort of probably, as you guys remember, right, a lot of times when we do elimination chemistry, when we simply take this molecule and we treat it with, say, for example, a base, like let's say sodium hydroxide, right, that's sort of not really sterically congested or anything like that, which one would you expect it to get normally? Bottom one, right? You'd expect the more substituted alkene, right? That's what you would normally expect to get. One of the things about the Hoffman elimination is that you've got a really big and bulky leaving group. And for those reasons, in the same way that a big bulky base will provide the sort of thermodynamically stable alkene, in the case with a big bulky leaving group, it's the same sort of concept. Even if it's a smaller base, it doesn't want to go to the more sterically congested guy here. And so you actually won't get this one. You'll end up with the sort of kinetic elimination product. So Hoffman elimination, that's one of the special things about a Hoffman elimination, is it's a leaving group that's a big bulky leaving group, and for the same reasons that we saw bulky bases leading to the more accessible proton. In the case of a Hoffman elimination, you see a very similar trend. Okay, but again, you can certainly see it behaving as a nucleophile. So again, if this is sort of on the milder spectrum of the leaving group, on the stronger side of the spectrum of a good leaving group is making it into nitrogen gas, or sorry, making it into a nitrogen-based leaving group, right? And so, you can't really get too much better of a leaving group, right, than sort of nitrogen, right? Like, you're not, it's a gas, it's going to leave as a gas, it's also got this positive charge on it. So for all these reasons, nitrogen as a leaving group is fantastic. And so there's a lot of interesting chemistry that you can effectively do once you have a nitrogen leaving group. And the way that you do this is you take this and you treat it with sodium nitrate, I think it's called, NaNO2, and HCl. Okay? You can also see it as the sort of acidic form of that, but usually this is you weigh out and you add a little bit of HCl to generate the active compound, which is HN. Okay, which is effectively this. That's going to be the active form. And if we go through the sort of mechanism of what's happening here, it's effectively going to be a dehydration process. Okay, so similar to before, what we can imagine happening is you can start to protonate this, right, or protonate this, for example. Nitrogen is then going to be able to add in. Again, there's different mechanisms that you can get there, all of which are legitimate. But from this sort of intermediate, this is one intermediate that you can draw. You can also draw it directly onto the NO bond as well, and the double bond O. Again, that's just sort of leaving that group there. But formally, what's going to happen here is you're going to do a series of dehydration processes. Okay, so however you want to draw the mechanism specifically. Right, you're going to leave water. Again, there may be a slightly different mechanism that you could use to get here, but it's the same kind of idea. Right, and then you're just going to get the same thing again, right? This is going to go and pulp out that guy. That's going to get you your product. Okay, so formally what it is you're treating it with a nitrogen that effectively has a couple water molecules on it. So you can effectively add in, you've got hydroxyls there, and then you can effectively just dehydrate that system, okay? And again, you can imagine another mechanism where you go to the sort of the NO double bond as well, but same idea, it's, they're both valid. Okay. Now, where you see this done a lot is if you're just going to take an alkyl leaving group and you're going to treat it with some type of nucleophile, you might not necessarily need something so strong, but where you can find a lot of value in having nitrogen leaving groups can oftentimes be, see quite a bit actually with aromatic chemistry. So we talked the other day about benzene, for example, right, having that triple bond in the benzene group. And I think I showed an example of where this was the intermediate that was sort of used to generate that, again, because it's such an amazing leaving group. So you will see oftentimes aniline generate these, what we call, I forget what the name of them is, like, they have a technical name, it's like arene, azido, something or other. Basically, it's just a benzene with a nitrogen leaving group on it. And again, there's actually some versatility here. So what you can do is you can take this, and you can actually swap it out with, say, for example, halogen. Again, we'll see even more versatility with halogen. So if you just treat it with, like, let's say, what do I have here? Some type of iodine source. I actually have, say for example, HCl. What you can actually do is you can switch this out with the chlorine molecule, or say for example iodine. I think you can actually do this with like, the book talks about it with like copper iodide, HCl, say copper chloride. A lot of different halogens you can swap this out with. And we'll see with halogens, we've already seen their versatility in other instances. The next chapter that we're going to discuss will be cross-coupling, and aryl halides are huge in cross-coupling chemistry. The Nobel Prize is effectively won from the chemistry that can be done with aryl halides. And so you can sort of see this would provide entry from anilines, which you might be able to get access to and then convert them into halogen-containing molecules. Another thing that they sort of show is H3PO2, if you just want to get rid of this nitrogen altogether. If we have time, I'll go through sort of mechanism of this one, because the book doesn't discuss, it's actually not really known, but I know that I mentioned it on the worksheet. But if you just want to get that off altogether, yeah. Over here? Oh, I see what you're saying. Should the chloride be there in terms of, yeah, let's with the time, that's a great point, and we're going to bring that up. We'll bring that up next class in terms of regiochemistry. Because, yeah, Felix just brought up a fantastic point that I think we'll get to next class. Having to do with the mechanism of how this actually goes to this and what the regiochemical outcome might become. That's important. And finally, again, there's just lots of other nucleophiles, like, for example, lithium cyanide. You can go ahead and add it to this as well. Okay, so this is just an example with the time that we're dealing with right now. This is just some examples of electrophiles that you can basically take amines and turn them into, and some of the chemistry that goes on with them. We'll basically spend all next class discussing chemistry that's like this, converting amines into some leaving group, and then the chemistry that can effectively result from, and as sort of Felix brought up, the sort of some regiochemistry that might be involved in some of these other processes. So, all right, with that, see ya.